Okay, number 21. This question asks which best describes the air we breathe and the water we drink, assuming that that water is coming out of the sink. Well, we talked a lot about this early on in the year. The water that comes out of the sink is a mixture. It's not pure water. It's got all kinds of stuff dissolved and dissociated into it. And so it's certainly a mixture. And so is the air we breathe. Remember that the air is a mixture of nitrogen gas, oxygen gas, there's carbon dioxide gas. So there's a bunch of other stuff that is, we breathe in a mixture of gases. So certainly it's one of these two answers here. And I think the best answer is a homogeneous mixture because, you know, the air is a relatively consistent mix of these things. I mean, there's more of certain things than there are others, but essentially, you know, the air's got uniform properties, and that's what we think of when we think of homogeneous. Okay. Number 22, this says if the daily dose of a certain medication is 125 milligrams per kilogram, how many grams of that medicine per day are needed for a person that is 150 pounds? So what this is just saying is that there's a small amount of medicine given per kilogram of mass. And so, you know, if you were 1 kilogram, if your body mass was 1 kilogram, if you were 2.2 pounds, then you would take 125 milligrams per day. But you are many more than 1 kilogram, and this person is 150 pounds. So I would suggest first probably just let's think about how many pounds or how many kilograms this 150 pound person is. So I would probably say 150 pounds, and I would convert that into kilograms by saying that for every 1 kilogram, there are 2.2 pounds. And so we can cross off pounds. We've converted now to kilograms. Let's do the math here. 150 divided by 2.2. And that is, so this person is 68.18 kilograms. Okay, so for every kilogram, this guy is going to need 125 milligrams. So I would just, you know, at this point say 125 milligrams per kilogram multiplied by the number of kilograms, 68.18, and this will give you your answer. Okay, so the 125 milligrams, remember this is in milligrams, times the number of kilograms that this person is, that gives us 8,522.5 milligrams per day, right? This question complicates things by asking how many grams of that medication are there. So if we're going to convert between milligrams and grams, this is we're dividing by 1,000, and so for every 1 gram, there's 1,000 milligrams. So we just simply have to divide our answer by 1,000, and that gives us 8.5225 is our final answer. And that is the total amount of medicine that this person would take over the course of a day if they were 150 pounds, okay? All right, 23. Okay, this one's a brute. Okay, so 23, you're gonna see a question like this. It says, which of the following metric measurements is smaller than 3.5 milliliters? Okay, so I've written some things out for you that you should take note of. I would take a moment to get these put down on paper because the strategy here is really to take all 4 of your options and convert them into milliliters, and then you can sort of make your decision about which one is smaller than 3.5. But the conversion between those is kind of rough. So let's go ahead and take these in turn. We'll do these right here. So we have been given 3.5 times 10 to the 6th nanoliters, okay? And there are there are a billion nanoliters per every milliliter. So let's go ahead and do this. We got 3.5 times 10 to the 6th nanoliters. And for every 1 milliliter, there are 1 nanoliters. Okay, so we cross off nanoliters, we make this division, and this is going to look like this. 3.5 times 10 to the 6th divided by 1, and this gives us 3.5. So this one here, this is equivalent to 3.5 milliliters. So that's not less than 3.5 milliliters. These are the same amounts here. Okay, the next one here, 350 microliters. This little weird symbol here that looks like kind of a U with a little beard on it right there, that's a microliter symbol. And here's the conversion here. For every 1,000 milliliters is a milliliter, okay? So let's go ahead and do our dimensional analysis. We got 350 microliters, and we want to convert that into milliliters. There are 1,000 microliters for every 1 milliliter. So this is just 350 divided by 1,000. And that is 0.35 milliliters, so that's definitely less. We could probably stop right there because we know that we're less than 3.5 milliliters, but let's go ahead and convert these other ones too, just because it's so much fun. 35 deciliters, so for every 100 milliliters is 1 deciliter. So let's use that conversion factor to convert 35 deciliters into milliliters. So there are, for every 1 deciliter, there's 100 milliliters. So this is 35 times 100, and that is 3,500 milliliters. Oof. So that's much bigger than 3.5. And then finally, 0.35 liters. Here's your conversion factor. For every, there's 1,000 milliliters in a liter. So we would say 0.35 liters. 1 liter is 1,000 milliliters. And let's do the math here. This is 0.35 divided, times 1,000. This is 350 milliliters, okay? Okay, so here are the options all converted into milliliters. Label this one. So the only one that's any smaller is this one here, B, okay? And that's the strategy you should use, yeah, okay. Number 24. Okay, so 24 is one we did not talk about this when we looked at Lewis structures. 24 asks for a number of resonance structures for this carbonate ion. So this is the structure for a carbonate ion, and the polyatomic ion carbonate looks like this, and it's got this bracket around it because that's what you do with a polyatomic ion that you've drawn the molecule for, and it's got its -2 oxidation state out here. So really a resonance structure, what that means is that it's just another way to draw this molecule so that it's the same structure but built slightly differently, and it's all about that double bond. And so this is a resonance structure for this one. Carbon double bonded to oxygen and single bonded to these other oxygens. That is a resonance structure. You can see it's the same deal. We've still got all these electrons here. And you can see that it's still the same structure, but it's just a different way of drawing it with the double covalent bond in a different place. So the other resonance structure that we could have here looks like this, with the double bond down here to this oxygen, okay? And again, it's just a different, it's just a different way of drawing the structure by moving the double bond around. So if I were answering this question and it said how many resonance structures are there? There are 3. Count them. 1, 2, 3. There are 3 resonance structures for that molecular structure. Okay. And number 25. 25, this is all about our conversions between hydroxide concentration and pH and pOH and things like that. So this is where you're going to use this that you have in your notes from class. So go ahead and find that to answer this question. And the kicker on this question is that it gives you a temperature. Just forget about it. Just don't mind that it's 27 degrees. pH and pOH and hydrogen concentration and hydroxide concentration, none of these 4 things in the corner here are affected by temperature. So don't worry about that. You might see that, and just don't worry about temperature, okay? So let's just use this here. We've got our hydroxide ion concentration, and we want to know what the pH is. And so here's our pathway. We've got this. That's where we're starting, and this is where we're ending, right? We want to get from here to here. So we're going to follow 2 different functions. First, we're going to take the negative log of our given hydroxide ion concentration. That's going to give us our pOH. And then we're going to take that away from 14 to get to pH. Okay, so let's go ahead and do that. So we are going to do negative log of 3.4 times 10 to the negative 5th. And let's see what that gives us. So remember, all you do is just the negative symbol, log button, and 3.4 times 10 to the power of negative 5. Close the parenthesis, and that gives us 4.469, okay? Okay, that is the pOH, okay? So we just went from here to here. So now all we have to do is take that away from 14 to get to pH. So 14 minus 4.469 equals, this will be our final answer. And that's going to give us 9.53. Okay, that's your answer. So it's all about just following the pathway, right? Follow those arrows to get from where you are starting to where you're ending. All right? Good.